I appreciate your trying to help us stay on time. I'm going to turn this over now to our second block, and moderating that block is Paul Singh. Paul Singh is from the University of California in Davis. He's a distinguished professor emeritus there, and he's also a member of the National Academy of Engineering. So Paul, thank you.
Thank you, Jim. Can you see the screen, or?
We can see you.
Okay, would you like me to get started then? Or?
Yes.
Okay, thank you. Well, thanks, Tim, again. I would also like to extend my warm welcome and greetings to everyone taking part in our forum. We heard from our previous speakers about the characteristics and challenges of the current, mostly linear food and agricultural systems. In this second block of presentations, we will examine how transitioning to circularity in these systems can help towards the goals of sustainability and resilience. Now, I believe our first speaker is not online yet, so we will be moving to the second presentation, and that will be a perspective on transforming subsystems into nature-inspired components for circular economies. And our speaker is Bruno Basso. He is the University Foundation Professor at Michigan State University. Bruno?
Hello, everyone. Hope you can see my screen. It's a great pleasure for me and a privilege to be able to share some of my thoughts on this very critical aspect of the challenges that we face. The goal of my talk is really to be able to propose a set of solutions that mostly deal with digital agriculture. And so, as we all know, we are living through it. I mean, we're all witnessing the possibility of this advancement being used on the farm, at least some starting to, and for example, pretty revolutionary robotics, be able to put water on specific parts of the fields, or applied by drones, and possibility of monitoring rate of change in growth of plants through drones and so on. One of the things this has been possible has already been mentioned by Jimmy earlier, through the possibility of be able to monitor. John Deere has really led the field in this, be able to have a GPS mounted on the combine. And so we have now the capacity to observe yield variation across. And it is done on a large percent of the farm in the US. And in fact, I am, to be sure, the word subsystem, I'm really going to address most of this solution applied from the farm to the gate, at the farm, basically field level, not dealing much with the supply chain. But there are a significant amount of solutions that we could propose. So the difficulties for a farmer to implement something that even to them could be appealing, saving inputs and increase profitability, it's really difficult unless you start bringing the system into play. And that means, using models, advanced analytics, such that each single pixel can be analyzed separately, and you can really understand through time how these fields vary. And so I had the capacity in the last few years in my lab to develop this yield stability concept and maps, even though the concept is not new, it's been developed several years ago already, but the possibility of understanding that parts of the fields are very efficient. So while the digital technology is leading us to a greater efficiency in the use of resources, and also given us the opportunity to identify really high inefficiency, the one that basically have caused all these challenges. And the problem with just depending on yield maps is, first of all, they're not everywhere and often maybe of lower quality or not be able to be shared, but they can still be used to validate independent approaches like the one that I've developed using satellite imagery. So this is an important preamble of, the introduction of the solutions, because now we are basically able to characterize variability on every single piece of any single piece of the land at 30 meters or 10-meter resolution now, to quantify the variability. And so this crowded slide here, just to give you a little bit of the methods, uses historical images and has evaluated the changes of every single pixel in remote sensing before the signal of the plants saturate, to see if it was always higher compared to the neighbor and higher compared to the rest of the field. And so the good news is, as shown, we're now we've been able to quantify 50% of the field that constantly high and stable with a very high nitrogen use efficiency, 75% nitrogen use efficiency. 25%, unfortunately, 25% is currently constantly underperforming. And so the impact, as you see, is significant. 1.1 teragrams of nitrates, then it goes into water bodies, lots of money, significant 700 millions of US dollars wasted, energy and CO2 evolved. We also have the capacity now to identify the impact of climate variability. So areas that they're more vulnerable to water deficit versus areas that they have possibility of accumulating water. So basically the unstable zone, these zones that depends on fields. So how do all this, come together into a more of an analytic and again, solution-based? So the other thing is, from this analysis of yields and environmental impact, the farmers are the critical element, the stakeholders to implementing decisions. So it doesn't do any good to have a very precise GPS unless it solves a problem to someone. And now we're finally getting attention because the level of knowledge at the subfield scale is able to give us the possibility of understanding this profit stability. So how stable in terms of an area is in delivering the economics. And so as you can see in this yield stability maps on the left, 11 years of corn data converting into, because some is soybean in between, 7 years, there are very large parts of the fields where the farmer loses money. And this is what the next phase is. We've been able to identify where these low and stable areas with a high level of precision and accuracy. And so the number that we have analyzed, out of the 80 million acres of corn, there are 23 million acres of low productivity areas. Some of them we know exactly where they are, as you will see, are located in the middle of the field. And these are areas we had the threshold of greater than 1 acre. And 7.5 million are on the edges of the field. And so if we were to convert this low and stable zone in alternative management through digital ag, either reducing fertilizer or going to a drastic change of precision conservation, as you'll see in a minute, there is a substantial amount of benefits, ecosystem services. Greater nitrate leaching reduction, 1.1 teragrams, greenhouse gas emissions in range of 3 to 5 parts per million altogether, so very large amount of CO2 non-emitted, and carbon sequestration, because this biodiversity crop, that they basically native vegetation, will not be harvested. They have, they are a sink of CO2, perennial root system with all the benefits of biodiversity. So this concept of, the nature-inspired elements, you go from the knowledge of at subfield, profit stability maps, converted into increasing biodiversity in the areas where low and stable areas can be, again, alternative land use, and leaving the high responsive areas to input, such that we can continue to produce yield and even push the envelope, because we're still far from closing the yield gap. And so that variable rate optimizer allows to get the greatest benefits and response of nitrogen, reducing environmental impact, in addition to seeing more profitability from either incentives from the government or carbon credits. So this is an example of greater carbon accumulated in if we were to plant this sorts of thing in marginal land. I'm about to wrap, Paul. This is just to show that now the capacity of, this is not a detailed economic studies, but we have a very good understanding of the areas that they lose money. And the ultimate goal is really linking areas of responses that can even go all the way to avoided emission quantification, to be able to scale this to precision conservation across the entire, Midwest, and calculating carbon credits, whether you do reduced fertilizer on the low yielding areas, or you either go all the way to precision conservation. So to conclude, going from precision conservation, the subsystem, now to reach circularities, this to me starts by choosing the right piece of land, because you don't waste some of these resources. And I may not have all the time to go over these complicated slides, but I list 2 critical papers about circularity and technologies that allow us to basically improve the sustainability of the system by new genetics, use of digital ag, bio, microbes or bioengineering, and ultimately electrification of the overwash. So with that, I'll look forward to interacting in the discussion, and I want to thank the investors, the funders, and the lab for all this work. Thank you very much.
Thank you, Bruno, for sharing your perspectives on the farm of the future with examples of novel technologies for transitioning to circularity. I understand that our first speaker, Luis Fresco, is now online. So the provocation for this block is going to be given by Luis Fresco, president of the Wageningen University and Research, the Netherlands. Luis, we look forward to your comments.
Thank you, Paul, and hello, everybody. It's a great honor to speak to you. I am indeed the president of Wageningen University and Research, but I'm also the president of the Federation of our engineering universities in the Netherlands. And in that sense, I also speak a little bit on behalf of my colleagues in more esoteric fields like thermodynamics and so on. So I was asked by Jim and others to really be provocative. And I hope that doesn't mean you kill the messenger. It really is intended to provoke you into thinking and provoke us all, including myself, into getting a better story on this whole area. So the first question I want to ask is, what is really the role of an engineer today? I think engineers are something different from fundamental hardcore scientists, also different from economists or social scientists. Engineers are people who are looking actively for solutions. And that means that you, by definition, you always have to collaborate, not just between disciplines, but very much also with the private sector, with society, with governments, and so on. And one of the reasons why I think Wageningen has been so successful and tops all the rankings all the time is that we have this continuous dialogue with society, with the private sector, and with government on what solutions are needed. And so I would say an engineer is somebody who wants science for impact. Okay, that's your first provocation. But the second one is immediately, yes, we can have partnerships with the government and with private sector entities and so on, but engineers are not a bunch of people loading the supermarket shelves. There is not such a thing as just a pick and choose approach where a government can put in $1 on one end and then say there comes $1 of impact on the other side. I want us to have room as engineers to also do the unthinkable, or think the unthinkable, or make the invisible visible, to have room for serendipity, to have room for things that are not ordered in advance. It's often the least suspected solutions that become really very powerful, and we only need to think in our area of the invention of the microwave, or even the invention of these yellow sticky pads, to see what potential there can be in failures. So an engineer is somebody who is for science with impact, but also who is the guy or the girl for masterful failures. And that is something for which we generally do not have that much room in our institutions. Thirdly, let me provoke you even more. I'm not sure that circularity really exists. or even at the planetary level, it's still thanks to the energy from the sun that we have a system that actually works. But nothing is really circular in the sense that there are no losses at all. And the term circular food systems or circular economies has become very, very fashionable. But actually, I think it's up to us engineers to really make a good calculation of the degree of circularity that's possible, and at what scales does circularity actually make sense. To try to get too much circularity at a low level, say at farm level or even at city level and so on, I think it's going to be quite destructive and very expensive, both from an energetic point of view as economically. Brings me to my next point, which is I think we should think more about trade-offs. There are no win-win situations, or very few. And every choice means that something else cannot be done, because exactly there is no circularity, because resources are scarce. And so making visible these choices for governments, for consumers, I think is going to be really important. There are very few win-win situations. If you look at them carefully, they usually do not hold up. And this is particularly true in difficult areas like increasing land use intensity, protecting biodiversity. They come with costs, with a hidden cost that's often difficult to know about, but we must really make those more visible. Then I think the key word for the future for us as engineers is the word precision. I think the current two big developments in our fields or adjacent to our fields are the improvements in genetics, particularly, of course, precision gene editing, and the improvements in big data, robotization, and so on. That means that all along the food chain, from weather and soil data all the way to the consumer, we can have a much more precise idea and track what has happened to every single part of the chain, including all the material flows and so on. And we are now experimenting in Wageningen, for example, with robotization, data-driven, which allows us to have mixed crops again and have an individual treatment for every single plant and have a much better use of the land, of water, of any protection and so on. And I think precision also extends to the consumer. It will not be very long before our watches will tell us not just the time, but also not just our blood sugar levels, but also our failure to have the right micronutrients and so on. So precision all along the chain and traceability is going to be the story. However, we're not about linear chains again. And so that's my next point. We are about circularity perhaps, but at least we are about systems. And it's no coincidence that the upcoming Food Systems Summit in New York of the UN in 2 weeks' time is about systems. It's the first time the UN actually talks about food systems, and it really means encompassing everything. But we also know that systems, of course, are very poorly defined, and that it's always a matter of where do you put the system's boundaries. I've rarely heard more nonsense about food systems than in the last 6 months preparing this summit, not because people are ill-intended, but because people don't understand what systems are. And at least this is the bottom line. There is not one food system. There are thousands, tens of thousands of food systems. And we better get them clear in our minds what the differences are, what are the comparabilities and what not. Then last but not least, knowing that I'm not allowed to take a lot of your time, what do you think is our most sustainable resource? Think about it a few seconds. I think our most sustainable resource is actually knowledge. It's the only thing that you can share without it making it less or using it up. And in fact, if you share it, it multiplies and it actually improves and increases and becomes better for you and for everybody else who uses your knowledge. So I'm a firm believer in sharing knowledge, even to the extent that I announced 2 days ago at Wageningen at the opening of our academic year, that we will give away the licenses on our CRISPR-Cas or a specific set of CRISPR-Cas licenses free to all those who have non-profit intentions to improve food production and improve sustainability. And I think that's a major step in terms of really doing something differently. it's often said we need a paradigm change. I don't think there are lots of paradigms to be changed. One has to be careful. But sharing knowledge and doing that in such a way that others can use it, I think is the greatest riches that we could give to the system and to our colleagues, particularly in the Global South. So these are my provocations. I will be hanging around if you have any questions or ideas in the chat or whatever. Thank you very much, Paul.
Thank you very much, Louise. Those were excellent comments, and I'm sure we will have a good discussion. So for our next presentation, when we look at transformations, it will be helpful to know more about how readily producers accept these innovations that we are talking about. Our next speaker to address agricultural solutions to global challenges, producers' perspectives, is Ernie Shea, President of Solutions from the Land. Ernie?
Folks, my name is Ernie Shea, and I have the good fortune of working for a not-for-profit organization that is led by a group of very visionary farmers, and they are working across the country, actually across the world, helping facilitate conversations about the future of agriculture. And it's a conversation that is really about a 21st century definition of agriculture. And we have been exploring how we can be relevant in the 21st century in a way that enables agriculture, enables producers to be recognized, valued, and compensated for all that they do, for all of the goods and services that they provide. So our conversation has evolved from how do we produce food, feed, fiber, and energy to the realization that we do much more than that. We produce all kinds of other goods and services, many of which are defined as ecosystem services. And this reimagining, this thinking out of the box in terms of how agriculture can redefine itself is what's been really exciting as we've had these conversations across the country and the world. And as we've been exploring, how do we become more relevant, more valuable, we've realized that there is no shortage of ideas, of folks with solutions. There are folks that are promoting conventional approaches, agroecological systems, regenerative systems, the precision agriculture systems, the list goes on and on. And what we have come to realize and appreciate is that circular systems that utilize multiple innovative approaches really can enable sustainable agriculture and food systems. And our partners at the American Society of Agriculture and Biological Engineers have been working with us trying to find ways to help better communicate how we talk with farmers about different approaches to farming. And what we've been focusing in on is this transition, or this transformation really, from a system that is defined as linear, where we are taking, making, and disposing, to a system that is much more circular, where we're designing, producing, distributing, consuming, and recycling. It's a much different approach. So where have we been having these conversations? One place has been in the state of Iowa, where we have been working with the Iowa Smart Agriculture Group and helping them have a conversation about the future of agriculture in Iowa. And it began with an honest assessment of how are things going. And this word cloud captures what we heard from these leaders. They recognize they've been on a path of continuous improvement, but there is still room for more improvement. And there was a lot of discussion about the need to improve resiliency, improve and strengthen diversification. We talked earlier about how our systems are leaky, but they have put all these together into the realization that there is no one silver bullet and that we need to find this different way forward. And for them, it really is about circularity. So there's a couple of examples that I wanted to shift to because there is no one circular system approach. There are many types of circular systems. And here's 3 quick examples that we've seen in the state of Iowa. The first is at the farm scale level, where we have an example of Kelly and H.A. Blair, who are now in a 15-year evolution of a farming system that's gone from conventional full-till corn to one that involves no-till soybean production, minimum-till corn, cover crops, oats, alfalfa hay, cattle and hogs. It's become a very diverse operation. And what they are really utilizing are the circularity principles, where they're recycling manure into fertilizer. They're using cover crops to improve soil fertility. They're reducing the need for purchase inputs. And this is just happening at the farm level. The Gasser farm to the right, down in Corning, Iowa, where Ray Gasser and his son Chris are farming at about 5,400 acres. It's a corn soybean farm, but they've been no-tilling, full no-till since 1991. They're now deploying and utilizing cover crops across more than half of their acreage. And as an example of the circularity at the watershed level, the corn that they sell is sold into a biorefinery, an ethanol plant that produces a renewable fuel that also produces dry distiller grains as a byproduct. The DDGs go to neighboring livestock operators who feed it to their cattle and raise protein for human consumption. The manure then is brought back to Ray's farm and applied as fertilizer. And he calls this the circle of life approach to circularity at the watershed level. The last example I'll touch on today is Brian Seaver's farm in the eastern part of Iowa, where he is working really to dramatically expand his beef cattle operation using a integrated system of multiple technologies, including anaerobic digesters. He's got two 970,000 gallon digesters that process 60,000 gallons of manure a day. And through that, they're producing renewable natural gas. It's being sold into the California market at a premium price due to the low carbon fuel standard. So we have a national application. And the other thing that's exciting about Brian's work is that he's created a market for cover crop residues, where neighboring farms who've been struggling to figure out how to pay for cover crop cost insulation can now be compensated for what was something that was just cost. Now there's value in that, and they're moving forward with an opportunity to enhance the effective functioning of the digester. So that's exciting. So to wrap up, what this is really about is a 21st century agricultural renaissance, where we're helping farmers think out of the box and explore a new way forward. And we've heard over and over again that the policies and the programs of the past are not going to meet the needs of tomorrow. And we need uncommon collaboration. We need innovation and technology, but we also need the indigenous knowledge that farmers have been building and expanding upon over the years. So for us, a circular approach makes a lot of sense. And we're going to be working over the course of the next couple of years, bringing this conversation into the agricultural thought leader space, helping them process and understand it. And in doing so, hopefully, we'll move to a more widespread adoption of these circular systems. So with that, I'll stop and give time back.
Thank you very much, Ernie, for your comments on the potential role of producers in developing acceptable transformations that are more circular for greater sustainability and resilience. In assessing the technological innovations noted by our speakers today, we should also consider the importance of including social, economic, and policy dimensions that incorporate circularity of supply chain options. In our next talk, we will hear about integrating socioeconomic and policy aspects across scales. The perspective will be given by Tom Hurtle, Distinguished Professor of Agricultural Economics at Purdue University. Tom?
Thank you, Paul. Just getting my sharing down here. Is that looking okay, Paul?
Yes, yes.
Great. Well, it's a great pleasure to be here today. It's really fun to be the economist on this panel of distinguished scientists and engineers. In fact, over the past decade, as most of you know, Purdue's a big engineering school, and over the past decade, I've been teaching students from across campus and many, many engineers, graduate students in a course on global sustainability in the food system. And in so doing, I'm going to appreciate the fantastic creative solutions that these engineers and scientists bring to this challenge. But I've also come to realize that there's often a missing piece in their analyses, and that missing piece has to do with markets and the role of markets bringing together supply and demand, determining prices, and that is an important part of the puzzle that we need to solve as well. So I'll be drawing on one example in this talk, and it's based on food, energy, water system work, a near and dear topic to Jim Jones's heart, I know. And it's been funded by, this work in general has been funded by National Science Foundation, also Department of Energy, Peaches Project, and USDA. So I want to think about circularity across scales. We've heard a lot right from the beginning of the talks today about global forces, population, 10 billion people, et cetera, changing dietary patterns. So these global forces are indeed driving a lot of the local sustainability stresses we observe, and we heard about that from WWF perspective, for example, the conversion of forests, increased fertilizer applications, and so on. So global forces driving local stresses. And the character of these stresses vary tremendously across locations. And we've seen examples of that at very fine scale. But what we haven't heard much about is the way these local responses can feed back, market-mediated effects can feed back to regional, national, and global levels. And I'll be emphasizing that today. So think global, local, global here. The case study is based on a publication published in Environmental Science and Technology. This is joint work with some civil engineers who work on power systems. They're at Penn State, Chris Kucharek, the head of agroecology, agronomy at University of Wisconsin, and several colleagues from Purdue University. We were very interested in the circularity potential coming about from here we sit in the Midwest. There's a lot of biomass growing every year, and a certain amount of corn residue that could be harvested and used to co-fire power plants. In particular, coal-fired power plants, which are a big source of greenhouse gas emissions in the US and elsewhere. So the idea is, why not take some of that biomass, co-fire the power plants, prolong their economic life a bit, and also reduce emissions. And so this is an idea that surfaces periodically, and in many states have this in their environmental plans within the US. So I want to examine this kind of circularity in the context of overlapping markets. And there's a market for electricity in the Midwest, the Midwest Independent Systems Operator market, and that's what our power systems colleagues model. It's a market that clears almost instantaneously over time. The corn stover market, which involves these supply circles you see on the map, with power systems sprinkled, power plants sprinkled across the landscape, land markets, and then the corn market, which is virtually is a global market. So we found, one of the interesting things we found in this study is that if we just left it to the power system engineers and said, in particular, those just analyze this sustainability scenario. So we incentivize the co-firing through a carbon price, and analyze the power plants one at a time. Okay, that's not actually the way these guys do it. These are system-wide modelers, but many people look at these power plants one at a time. And when you do that, you vastly overestimate the extent of biomass demand. And why is that? Because a number of these power plants, in fact, 6 of the 8 in this region I'm focusing on here, cease generation under this regime. They're no longer competitive in this. They're competing against renewables and more efficient coal-fired power plants in the electricity market, and they're competing with other power plants for biomass within this supply circle. When analyzed as a multi-scale system, only 2 of the plants in this area are actually competitive and generate and sell electricity into the system. We also were interested in the consequences. We've heard already about the challenges of nitrogen use and nitrate leaching, water quality throughout this region in excellent earlier talks. So we wanted to analyze, collaborating in this case with Chris Kucharik, the implications for corn production and nitrogen use. And what you see emerging are within these supply circles, increases in corn production, not surprisingly. This is another new source of revenue. It's not just your corn grain, but it's also the stover now that you're selling. So this encourages expansion of corn production. And since you're producing more biomass, you're also producing more grain, and that flows into the markets and actually depresses corn production outside of these supply circles. Not a lot, but there's a response spread across a wide area. Within the supply circles, here you can see a characterization based on Chris's agroibis model and run at the grid cell level. So all of this economic analysis is being done fundamentally at the grid cell level and then feeding up through regional and national global markets. And you can see the two key agroecological relationships are the response of yield to the increased nitrogen, and that's most of these producers are operating on a pretty flat spot out there on this Gompertz curve. So increased nitrogen doesn't get you a lot more yield. You have to apply a fair amount if you want to boost that very much. And whereas those increases at the high level of nitrogen result in a lot more leaching. So it's a precarious spot that they're operating in right there, and any increases are potentially problematic from an environmental point of view. So what we have is the emergence of hotspots of nitrate leaching. So look at Southern Illinois, for example, an area that has a lot of coal-fired power plants, and already a lot of corn, a lot of nitrogen being applied, and a serious water quality problem. Nitrates leaching out and into the Mississippi River and into the Gulf, in fact. And so you can see that this environmentally motivated policy in this case has actually results in some serious hotspots in places where there's already an environmental problem, further exacerbating that. But if we analyze this, as most economists do, at the regional level or the state level or even the national level, you would have noted only a modest increase in leaching. It's really only when you get down to the grid cell level, only when you bring the economic analysis down to the grid cell level in collaboration, in this case with the agroecologists, that we see some grid cells experiencing increases as much as 60%, so a dramatic hotspot. So just to wrap up here, I want to just reinforce a case that's been made already here for transdisciplinary analysis, particularly in the context of global to local to global kinds of work, and thinking about these complex fused systems. This example has highlighted the potential for unintended consequences of policy. That was a point raised earlier today, the risk of unintended consequences in these complex systems. While addressing one environmental problem, global greenhouse gas emissions, we have exacerbated another one. And this raises it just highlights the trade-off issue that Luis Fresco raised earlier on. Economists are always bringing up these trade-offs, and this is another example of that. This comes about through market-mediated spillovers. So there are these four interacting markets, and you do something in one market, changing the demand or supply, and that spills over through prices into other markets and across the landscape. So I do want to emphasize the importance of cross-scale analysis, that these local responses, not only are they heterogeneous, but they can feed back to the regional, national, and global levels. And this is really a theme that we're really pushing now with a new five-year NSF project under their ExcelNet program. It's called GlassNet, and it aims to strengthen links just of the sort that we're talking about today between engineers, agroecologists, economists, climate scientists, many others are involved. And this is a network of network effort. So all the funding is going into facilitation of networks and early career scholars working within that. So there's a link here for those who might be interested in GlassNet. So thank you very much, Paul. I'll stop there.